Hey, AP Calculus students, Mr. Record here from Avon High School, and we're going to talk a little bit about straight line motion. If you are a member of my class and you're watching this on the day that it is assigned, you may have remembered that we briefly talked about objects that may fall from the sky in a vertical sort of straight line fashion. We're now going to sort of direct our attention to motion that's along a horizontal line. And what will probably be the case on the AP exam is that you will see problems dealing with motion horizontally so that we can sort of eliminate all of the laws of gravity and things of that nature. And as I've said to you many times before, is that you're probably more apt to see questions like that on the AP physics exam. So this is a great exercise here that you have on a worksheet that I'd like to take a look at here with you. It says a particle is moving along a horizontal line with position function as given. It says do an analysis of the particle's direction, acceleration, motion, which is going to be a new idea for us, whether or not its particle is speeding up or slowing down, and then do an analysis of the position. And I want to make sure that nobody is startled by the fact that when you see this S of t equation right here, that the fact that it does not appear as a quadratic form should not bother you. Again, these are not meant to be representations of objects that are falling from the sky that are affected by the Earth's gravity. So nowhere do you see sort of a negative 16 t squared coefficient or a negative 4.9 t squared coefficient there. So the rules that we have discussed about those particular types of motion is sort of out the window, but some of the calculus ideas are still very much going to hold true. So the very first thing that we're going to do an analysis of the particle's direction, we're going to find that we must take the derivative of the position. So the derivative, s prime of t, would be, of course, what we call v of t, the velocity, and we would get 3t squared minus 12t plus 9. Now, it's this derivative that is going to help us find out information about the direction. Now, how are we going to go about doing that? Well, there's a very important concept that I want us to be able to tackle here first, and that is to figure out when is this particle stopped, because some very interesting things may happen when the particle is stopped. Well, we can set this derivative equal to 0. And as I set this equal to 0, I'm going to do some factoring as well. We can pull out a 3, of course. And we can continue our factoring. And at the same time, divide by the 3 that's in front. And we would end up with values of time equivalent to 1 or 3. So at time 1 or 3, this particle is indeed stopped. Now, what are we going to do with that 1 and 3? Well, we're going to place those on a number line. And it's really what's going on around those times 1 and 3 that are going to give us our information about direction. So I'm going to sort of list out the function that we're focused on right now. That would be the v of t, and I'm going to use a line here. And on that line, I want to place some values. Now, I also want you to consider something here. When we're talking about this particle moving, I would like to define the very first moment that the particle does move as time 0. So I would like for you to always label the left end of your number line with a 0. You'll notice that that number line did not have an arrow at the left side, but it does on the right side. Now I would like you to place time 1 and time 3. It really doesn't make a lot of difference of, exactly where they're going to be located. It's obviously important that you put time 1 to the left of time 3. It would be nice if you put them on the number line in such a way that they were perhaps sort of maintaining the scale, perhaps. But it really isn't going to give you erroneous results if you don't put 1 and 3 in those kinds of positions. So something along this line would look just great. Okay? Now, we know that this particle starts its motion at time 0. We know that it stopped at time 1 and time 3. We want to know what's the velocity doing in between those times. So it is very easy to do a quick test value, picking some value between 0 and 1. Probably 0.5 would be about as good as any value that you could come by. And v of 0.5 is equal to, and if we go over to our factored form, I think we can find just as good of a piece of information here. And you'll notice that, oh, wait a minute, do we have to worry about the 3 here? Well, no, because I do not care. In calculus, we do not care exactly what the value of the velocity is in instances like this. We only care about the sign. Is it positive or is it negative? So if you were to plug in 0.5 for the t here and subtract 3, all you have to do is know that this produces a negative result. 0.5 minus 3. It's actually negative 2.5. Do the same over in the other binomial, plugging in 0.5 for t, and you can see that you get negative 0.5. So if you have negative 0.25 times negative 0.25, I'll get that right, negative 2.5 times negative 0.5, you're multiplying two negatives together. Hopefully I didn't confuse you at that point. So a negative times a negative, of course, is a positive, so you are going to indicate positive above the number line. Now I'm going to go ahead and draw as many little plus signs as I can fit on that interval. It doesn't make a difference if you draw 1 or 2 or 3 or 4, as long as you have at least one. I typically like to fill up the entire interval so that there's no questioning exactly what the sign is. Now, what that actually means is if our velocity is positive, we are moving to the right. Now, if you're a student in my class, perhaps you'll remember a few weeks ago when we used the vernier motion sensor and we had students come up in front of the class and walk away from the sensor, and we saw the graph of position over time, and you saw that that graph actually increased, thus had positive values going on to its derivative, and that would indicate the fact that you were moving away from that motion sensor, and I had set that motion sensor purposely up on the left side of my room so that you were actually moving to the right. Now, we're going to continue to do this same demonstration with a test value between 1 and 3. You can probably guess that 2 would be a very good value to test. Let's see if I can explain this pretty clearly. You're going to now plug 2 back into this this product of these two binomials. 2 minus 3 would be negative 1. 2 minus 1 would be 1. So you're talking about a negative times a positive. Once again, we don't really care what the value is. We just want to know what its sign is. So a negative times a positive is a negative, so we're going to write as many negative signs as we can on the interval 1 to 3. And then finally, to test something to the right of 3, you can choose anything. 4 will look great. And I think it's pretty clear that once again, when you go back into the t minus 3, t minus 1, you'll get positive 1, positive 3, positive times positive, which of course is positive, which this indicates that our particle is moving to the right. So from 0 to 1, we are moving to the right. From 1 to 3, we're moving to the left. And from 3 to infinity, the particle is continuing to move to the right. And that would take care of the first analysis, the particle's direction. Next, we want to talk about the particle's acceleration, which I will do in red. Well, in order to do that, I obviously am going to have to take another derivative. We've talked about this in class, but the derivative of velocity, or the second derivative of position, will be acceleration. And in this case, that derivative would be 6t minus 12. Well, much like your velocity analysis for direction, you're going to do the same type of thing with your acceleration. You want to figure out, first of all, when is my acceleration 0? When am I neither speeding up nor slowing down? And you would find that that would solve very quickly to give you just t equal 2. So I'm going to set up my acceleration number line. Once again, you'll have a number line quite like you did for velocity, where it would have an endpoint at the left side and an arrow on the right side. We would like to denote the very left side as time 0. And since time 2 is the only value at which we're truly interested, that is where the acceleration is 0, I'd like to put the 2 in a very logical location. You can see from the above number line, the 2 would be right between the 1 and the 3. So we can start our sign test at this point. And all I'm interested in knowing is the acceleration positive or negative? So we'll once again do some test values. A of 1 would be a great option here. Now we're going to be plugging A of 1, or 1, I'm sorry, into, we could just go ahead and plug it into that expression, 6t minus 12, or this expression, 6t minus 12. And if you do so, you get negative 6, which is quite the negative number, and therefore we can fill in negative signs up above the number line. As you can guess, we can flip a number to the right of 2. 3 would work great. We plug in 6 times 3 would be 18 minus 12 is 6. But once again, I really don't care if that's 6. I just care more or less if it's positive or not. And it is positive. So we'll move on positive, positive, on forever. Now what we have discovered here is that the acceleration is negative between 0 and 2, which indicates deceleration, and on the interval 2 on to infinity, a positive acceleration may indeed represent acceleration. Well, that's true to an extent, because we have this idea now called motion. And motion is the new one. Motion is the sort of a tricky one. With motion, you actually don't have to worry about taking any more derivatives, because to analyze motion, you're going to look at both the results of the velocity number line and the acceleration number line. So you're going to put your third number line down, once again with a endpoint on the left side, an arrow on the right side. And this time, with our motion being demonstrated in green, we want to take all of the values along the number line at which velocity was 0 and acceleration was 0 and place them on our motion number line. So we'll have a 0 to the left, and then our 1, and then our 2 from acceleration, and our 3 from velocity. Now where the motion is different is that you will not do any testing, because motion doesn't have sort of its own little equation to testing. Motion is just simply an analysis of velocity and acceleration at the same time. And the idea behind it is if velocity and acceleration have different signs, as you can see is going on the interval 0 to 1. Velocity is positive, acceleration is negative. If velocity and acceleration have different signs, then your motion will be slowing down. And you'll just simply write that phrase, slowing down. Now, depending on how big you make your number line, you might have to write pretty small. I wouldn't care so much if you said slow down. That would convey the idea. Now you continue to look at what's happening with velocity after time 1. Well, then velocity changes to negative, and it does so for a while, but acceleration, remember, after time 1, was still negative. Now, in this situation, if velocity and acceleration are the same sign, thinking that we're moving to the left, our particle is moving to the left with this negative acceleration, it's like a force that is pulling upon our particle, making it go even more so towards the left, and thus it actually makes the particle speed up. So you would say speeding up on the interval 1 to 2. Now later on, I'm going to show you lots of other applications that might make the concept of same signs for VNA speeding up, opposite signs of VNA slowing down. But for right now, this is our basic introduction, and I want you to get comfortable with the results here. So from time 2 to time 3, we noticed that, well, our velocity was still negative, say that would be in the interval 2 to 3, but then acceleration does something a little different. It goes positive. In fact, it will stay positive the rest of the way. So we have the opposite signs happening. So you would go ahead and say, slowing down one more time. And then, as you can probably predict, from 3 on to infinity, your signs are in agreement again. So we're back to speeding up. We are 3/4 of the way there. We have one final piece to analyze, and that would be the position. I'm going to have to scroll down just a little bit to get some room here. And for my position, I guess I can go ahead and use a different color. I'm going to use, how about purple? Let's try that again. Let's go with purple for position. All right, so how are we going to do this? Well, we're going to go ahead and use a very logical choice for a position identifier, and that would, of course, be our S of t. S of t, for like the last several weeks here in class, has depicted position quite frequently. Now, the one thing that is going to be a little different about your number line, I don't want us to think that the number line will start at 0, because that won't necessarily be true. Because position is not so much going to be measured in terms of time as we would think it would. The number line that we're about to lay down is actually going to stand for position. The values along this line are position values. That's very different from the previous 3 number lines where the values stood for time. So that being the case, what we need to do is figure out exactly what is the position of this particular particle at various instances during this analysis. Well, at various instances. Well, what we're talking about are at the time 0 and 1 and 2 and 3. So what we'll do off to the side, and I've got some room over here, we're going to figure out where this particle was at time 0. So all I need to do is go into the position equation, and I think it would be very easy to plug 0 in for t and see that you get -4. You're going to find out that plugging in 0 for these polynomial position equations is going to be quite easy, and that's where you're going to want to start. So at time 0, we're at -4. Well, you might ask, well, where really would I want to put -4 on our number line? That's a great question. Sometimes I don't always have the best answer for you, but I would avoid putting it anywhere way to the left side or way to the right side. I would say we could put it somewhere in the middle, maybe 1/4 of the way or 1/3 of the way from the left. It really doesn't make any difference, but I want to make sure that you realize that if indeed our particle does end up moving to the left, that we have some number line space to the left of the -4. Once again, I can't emphasize this enough. The values that you are placing on your S of t number line analysis are positions and not times. And to further demonstrate that, I would like to write the time t equals 0 right next to that position, and I will put a dot there. That's where we're starting. Now, since we're only demonstrating what's happening with position, we probably recall from our velocity that v was positive, as you can see from my arrow here, on the interval 0 to 1. So our particle would be moving to the, hopefully you're all thinking, to the right. So we could actually start to draw the motion of this particle. It's going to the right. Now, I don't want to get too overzealous here and try to draw that in its entirety because I don't know exactly when it's going to stop. Well, I take that back. I know when it's going to stop, but I don't know where it's going to stop. Now, if we think back to when it stops, that was at time 1, if you remember that from our analysis of velocity. So we need to figure out s of 1. Well, if you plug s of 1 into the s equation, you would get 1 cubed, which is 1, minus 6 times 1 squared, which is 6, plus 9 times 1, which is 9, minus 4. And if we work all this out, we end up with, negative 5 plus 9 is 14 minus 4, which is positive 10. So at positive 10, we would end up having a position where this particle would turn around. So we'll take this guy all the way to the right, and I don't know, maybe positive 10 could be right about there perhaps. We'll let positive 10 be that value. Okay, well, now we know at time 1, we're right here. Now what's going to happen after time 1? Well, as you can see, the velocity began to be negative, which means our particle's moving to the left. Now, to best demonstrate that, you can't really draw back to the left on top of your motion because it's really difficult to see the direction. So I would just suggest that you just do a little U-turn, start heading to the left, and we'll know exactly how far to stop whenever we figure out our next value of t stopping point. Well, that value of t stopping point was at time 3. So the position at time 3, this will be a little bit tougher to find, but the position at time 3 would be 3 cubed, or 27, minus 6 times 3 squared, that would be 6 times 9, or 54, plus 9 times 3, which is 27, and then our constant minus 4. Now, if you've got that far, you'll be able to do the arithmetic here pretty quickly because the 27s and the negative 54 will essentially cancel each other out, and I'm not so sure why I wrote equals 0. Please ignore that. And this would end up equaling negative 4. So that means that at time 3, this particle is going to have gone all the way back to where it originally started. That isn't typical with every single particle problem. In this case, it is. And then after time 3, all we know about the particle, if you would focus back to the v of t equation where I'm underlining the next plus, is that we are now moving to the right again. So you're going to turn around, and this guy is going to move to the right. And now I know exactly how far to take it. I'm going to take it as far as my number line will let me, because forever and ever after time 3, I'm moving to the right. And that would complete the analysis of this particle's motion. Now, before I stop, I want to mention one thing that students sometimes get confused by. Why is it that I only had to use the time values that were pertinent to the v of t analysis? Why did I not use time 2? Well, the answer to that is that we're not really considering how the acceleration of the particle is or the rate of change of its velocity. In the position equation, it is only about direction. And the direction, if you recall, was answered very explicitly in the v of t equation. Hopefully this will give you a great synopsis of how to analyze straight line motion. You do have, I believe, 3 other problems very similar to this on your worksheet, and then at the end of those 3 problems, you'll encounter some of the problems that we discussed in class from Chapter 2. Anyway, hope this helps. I'll see you next time.